Hello students, and in today's class we are going to talk about the Lewis concept of acid and base. What is the advantage of this Lewis concept of acid and base? Certain acids are donating hydrogen plus according to Lowry-Bronsted concept, but certain well-known acids which are not forming hydrogen plus as well as which are not donating hydrogen plus can be explained by this Lewis concept, which means certain substances, they are not forming H plus, they are not donating H plus, but they can behave like acid. Why? Those substances which can donate electron pair are called bases. The substances which can accept electron pair are called acids. So according to this Lewis concept, certain substances which can receive, otherwise which can accept electron pair are behaving like acids. Acids, what are acids according to this? Acids are the substances which can accept electron pair, otherwise pair of electron. So generally these are all electron deficient. The substances which are electron deficient, so that they can receive electron from the electron donor. And what are called bases? We can say the substances which can donate electron pair, which means these are all generally electron rich, so that there will be a coordination bond in between the acids and bases. I will take an example of acid now, electron deficient compound. We will be taking the boron. The atomic number of boron is 5 and electronic arrangement is 1s2, 2s2, 2p1. See the outermost cell of boron. It is containing 3 electrons in the outermost cell, so that it can share its electron pair with fluorine and forming BF3 molecule like this. After the formation of BF3, in its outermost cell, we are finding only 6 electrons. Actually, after the formation of a compound, it is expected to have 8 electrons based on the octet rule. The octet rule says that it should have 8 electrons, but it is containing lesser than that, only 6 are present, hence it is said to be the electron deficient substance. So in order to get the octet structure, still it is in need of 2 electrons, so it can receive electron from the electron donor. So BF3 is the very best example of acid. And what about the base? See the ammonia NH3, in which the nitrogen is containing the lone pair of electron, so that NH3, which is having the lone pair of electron, this pair of electron can be given to this, and this is the electron pair donor, hence it is a base, Lewis base. It is acceptor, hence it is an acid, the electron pair acceptor. The bond formed in between these two is nothing but coordination bond. So a coordination bond is formed in between the Lewis concept of acid and bases, in which this is the best example of Lewis acid. Boron trifluoride. The boron, its atomic number is 5. So the configuration is 1s2, 2s2, 2p1. The outermost cell is containing 3 electrons in it. Okay. And we can have the excited state 2s1, 2px1, 2py1 and 2pz is vacant. So after the excitation of electron from s orbital to p orbital, the boron is having 3 unpaired electrons in its valence shell. So the boron is sharing its electron with 3 fluorine atom and forming 3 covalent bonds like this. After the formation of covalent bond, it has got only 6 electrons in the outermost shell. Once a compound is formed means it must have 8 electrons in its valence shell. But in this case we are finding only 6 electrons. And hence, due to the presence of this 2pz vacant orbital, we can call this as electron deficient compound. Okay. Now this electron deficient compound should get electron from the electron rich substance. That's the reason why the boron trifluoride, which is receiving a pair of electron from the ammonia NH3, in which the nitrogen atom is having a lone pair of electron. This lone pair is given to the boron. The arrow mark indicates that there is a formation of coordination bond. So an addition product is made, adduct is made in between these two substances, and this is the substance which is receiving the electron pair, so that we can call this as Lewis acid. This is the substance which is donating the electron pair, and hence it is called as Lewis base. Okay, and we can have the other example for the same Lewis acid base concept. Okay. Some more examples of Lewis acid and base. You see, this is a electron deficient substance, namely AlCl3, and it is an ether CH3OCH3, which is called dimethyl ether, in which oxygen is containing the lone pair of electron. When the lone pair of electron is given to this AlCl3, we can have a substance as follows. I am writing AlCl3. Now this is going to make us a bond with this dimethyl ether. So the arrow mark indicates that the adduct is made, addition substance is made, and a coordination bond is formed in between these two. Likewise, the other example, carbon dioxide, C double bond O double bond O, CO2, when it is in contact with the calcium oxide. Calcium oxide, in which oxygen is containing the lone pair of electron. When it is given to that, it is forming an adduct as follows. It is nothing but calcium carbonate. So these are the additional examples of Lewis acid base. And we are going to distinguish between the Lewis acid and base, and the points are compiled in the form of table column as follows. Lewis acids and bases, how to compare them, and what is the major contrast in between the acid and base. That is tabulated here, the Lewis acids and Lewis bases. We have already discussed that the Lewis acids are electron deficient substances, and we were seeing the explanation for boron compound like boron trifluoride and aluminum chloride. In addition to that, beryllium fluoride is also electron deficient. And what about the Lewis base? Lewis base is always electron rich, which means the following type of substances: ammonia, it has got a lone pair of electron; water, it is containing 2 lone pair, the oxygen atom is containing 2 lone pair of electron; alcohol, in which oxygen is containing the lone pair of electron; ether, in which there are two lone pair of electron. Amines are having the lone pair of electron on the nitrogen atom. So they are all the best examples of Lewis bases. And all your metal ions like Fe2 plus, Fe3 plus and Cu2 plus. It is most common to see the coordination compounds like this. So you just consider K4 FeCN6. In this particular complex, Fe2 plus is the central metal which is electron deficient, receives electron from the Cn minus. So Cn minus is the base, Fe2 plus is acid. In all your coordination complexes, mainly the central metal is taken from the D block. All your D block elements are electron deficients. For example, Ag plus, Cu2 plus, Cr3 plus, copper 2 plus, Fe3 plus, plenty of examples can be taken. And all your anions are Lewis bases. You see this is the ligand Cn minus. In this complex compound, this is the electron donor Cn minus, which is commonly called as a ligand. So that ligand is behaving like a Lewis base, Cl minus, thiocyanato and sulfato, SO4 2 minus. And see the molecules with polar double bond. What are called polar double bond? You see the carbon dioxide on either side of carbon, there are two double bonds. One of the bond is sigma, other one is pi. Due to the electronegativity difference, there may be a slight charge difference in between the carbon and oxygen. So such kind of molecules are called polar double bond molecules. They are all ready to accept electron pair from some other substance called Lewis base. In opposite, molecules containing carbon-carbon multiple bonds, ethylene, acetylene, in these cases, apart from this regular sigma bond, we are having a pi bond. The pi bond is usually weaker. The pi electrons can be readily donated. So the electron donor is a base. So this can able to donate electron pair from the pi bond. And other one, the central atom in the following substances, namely silicon tetrafluoride, sulfur tetrafluoride. The sulfur as well as fluorine can expand its valence shell. Just see the sulfur tetrafluoride in which the outermost shell is containing 4 electron pair, 4 into 2 electron, which means 8 electrons are present, octet. But sulfur tetrafluoride, actually 4 bonds are there around the sulfur. Each bond can have 2 electrons, so totally 8 electrons are there. It can expand its valence shell, so it can able to form a substance like this, SF6, sulfur hexafluoride. Due to the presence of vacant d orbital, it is expanding its valence shell. It shows that in order to expand the valence shell of sulfur, it is acquiring some electrons. So it is ready to accept electron due to the expansion of valence shell. Likewise, silicon can expand its valence shell by receiving the electron due to the presence of vacant d orbitals. You see the opposite side, metal oxides like calcium oxide, magnesium oxide, sodium oxides. The metallic oxides are ready to donate electron because in these cases calcium is getting attached to the most electronegative element like oxygen. Oxygen is having the lone pair of electron that can be donated. So that's the best donor of electron pair. See the opposite side, carbonium ion. This is a tertiary carbonium ion. Carbon is surrounded by 3 electron releasing groups. So the carbon is acquiring positive charge, which means it can readily accept electron from the electron donor to make a bond between the carbon and the electron donor because the carbon is carrying positive charge. Carbonium ion, also known as carbocation. See the opposite side, carbanion, the alkyl group which is carrying negative sign. So it is the best donor of electron pair. So this is the compilation, the greater differences in between the Lewis acids and Lewis bases. So just by seeing this tabular column, one can understand the contrast or the differences between the Lewis acids and Lewis bases. So these are the details about the Lewis concept of acid and base. Is it clear? The other things we will continue in the consecutive videos. Thank you.